So today's session will be presented by Mr. Pranay. Uh, Pranay is a research assistant at FOSSEE IIT Bombay, and he is going to demonstrate some case study in the same domain. So over to you, Pranay. You can start your presentation. Thank you.
Thank you, Paris. Thank you very much. Thank you for handing over. So, good afternoon, everyone, or good evening for many. Continuing on the previous lecture, right now in this demonstration session, we are continuing to see how open foam has been used by our fellow mentors and fellow interns in resolving problems related to wind turbines. Primarily, we have good number of cases available. Very fine among them is 2D simulation of H-Darrieus type of vertical axis wind turbine, which will be resolved using transition turbulence model in OpenFOAM. To open it, we'll have to open this link. Uh, Maybe after this demonstration session is over, you can personally download it on your laptops and follow the steps I'll be showing to replicate it on your system. I'll be sharing the case link also, wherein I have modified some case files to enhance automation and to include interactivity while resolving the case. So this case was solved by Mr. K. Sri Satya Sai Sasank back in 2022 using OpenFOAM 2112. Moving back, so let's make ourselves aware of what the problem is. In this problem, the primary objective is to use a turbulence model named K omega SST LM. We'll be delving into it further, but this turbulence model is basically to capture both the laminar and turbulent transition together in a single case. And also, it studies unsteady aerodynamic loads, the wake structure, the vortices, the eddies, etc., which are a part of realistic operating conditions. Usually, 3D computational cost is very, very expensive. Uh, and 1D simulations provide a very faint and very unrealistic idea when it comes to turbo machinery. So that's why the case which has been done by one of a fellow intern was in 2D. The right side image, it shows a general schematic of the H-Darrieus. VAWT stands for vertical axis wind turbine. We'll be seeing how VAWT is different for HAWT. Where H stands for horizontal axis ahead. Uh, in the overall case, the case study proposer has made significant efforts to build concrete mesh. We know mesh is a very important part while resolving CFD simulation, CFD solution. So that's why the line hybrid mesh generation using snappy mesh, etc. And the flow velocity, we'll be discussing the boundary conditions too. Okay, moving on to next. Okay. This is the general schematic or the top view of the geometry and the overall domain. The airfoil used is NACA 0015, a symmetrical airfoil we all might be knowing from the NACA series. The chord length is 0.4 meter, the radius is 1.25. Inlet varies from 6 meter per second to 10 meter per second, accounting for the angular velocity of 15 radian per second. This rotation factor is important to model the counterwind flow. The model, as discussed previously, it is K omega SSTLM. Uh, it solves to equations that is basically gamma. We'll be discussing it turbulence conditions and the re theta. Basically, what happens is the solver continuously change based on the input provided from gamma and the transition Reynolds number, adjust the value, and thereby it is able to resolve both the transition and the laminar cases accordingly. Uh, the next line, gamma belongs between 0 to 1, wherein 0 represents a laminar condition and 1 is a turbulent condition. I'll be showing you each of the files uh, later ahead. When the starting condition is given, the wind turbine will be rotated very slowly. That's why it is important for laminar. And when it is shifting to a high speed or relatively higher speed, we'll be seeing different angle of attacks, which will be creating unsteady shocks. Could be it could be shocks or it couldn't be shocks, but unsteady vortices, unsteady flow. Boundary layers will be different. It can also happen in the initial part of the airfoil while it has been rotated or it is in a startling condition. There will be a boundary layer in the laminar flow, in the laminar region. Also, there can also be transition from laminar to turbulent in some other part of the airfoil. That's why to capture it effectively, it was the idea of the presenter and it was the idea of the intern to use this SSTLM model. It is noteworthy that K omega SSTLM is Ransby's turbulence model. It's similar to what K omega SST is. Just the difference which you will be seeing is two addition equations of intermittency and transition Reynolds number. Since Sarah has already discussed a lot on this, I'll just give you a gist on what types of wind turbines are. Primarily, we have two different axis based wind turbines. One is the horizontal axis, which we all are very familiar with. We have seen it a large number of times in the wind farms, in the countryside, etc. A vertical wind axis turbine is something, if I may, the axis is symmetrical. This is the axis of symmetry. Okay. And the rotation is around this axis. Unlike in the horizontal axis, the axis of rotation is among this plane. Okay. One interesting fact I got to know about this type of wind turbine is this was actually way back discovered or created, or kind of mechanism was created way back in the 9th century AD. That is almost 1100, 1200 years back. Uh, It was patented by a scientist, which I'm not able to recall, but in the year 1920, to use it as wind power application. I hope the striking difference is clear between a normal conventional which we see and which is a horizontal axis, wherein in this case we are sticking with the vertical axis wind turbine. Towards the left of the presentation, we can see different types of wind turbines available in the vertical axis mode. One is the Darius rotor, H-Darrieus, and helix. H-Darrieus is something which is something more common in the vertical axis wind turbine, which is used more practically, accounting for both cost, implementation, etc. And to read further on VAWT, I'll be sharing the slides, and each slide has something good links where you can read more on that on a conceptual level. Moving next. Okay, coming to the types of mesh. Since I presented a line wherein I said mesh is the utmost important part and the pre-processing step, and without mesh resolution, proper mesh creation, all the results which we will be going through would be considered baseless or would be considered incorrect, inaccurate, or we can come to some heterogeneous answers. So that's why it's important to have a better idea, very crisp and clear idea on when to use what kind of mesh, how to use it. We have to account for the computational cost involved and similar such factors which we are all familiar with since we are CFD professionals. And to those who are not familiar, I'll just bring out this also five kinds of mesh highlighted here. First is a chimera or the overset mesh. Here, what happens is we are describing a domain, uh, and we are setting mesh based on the individual component. We are stacking one mesh over another, unlike the conventional one wherein we use a continuous mesh. I This splitting of mesh and then recombining, what happens is we can be uh, very much precise in capturing flow around the whatever body we are trying to simulate primarily, and it can be considered to be very accurate, wherein what happens with the single continuous body fitted meshes, it becomes difficult to generate because of large parameters involved in the mesh metrics. It is difficult to control in the single continuous, but Chimera or the overset mesh helps us prevent that. Second is the Structured and unstructured mesh. Structured, we can model it very perfectly. It is good. Whereas unstructured is also very good, but it comes where how in what part and which region are we are interested in simulating the flow. Unstructured is basically in very useful to capture in regions where the curvature is very different, wherein the geometrical curvature is different or it is difficult to model. Adaptive mesh refinement, people who might be knowing shock, supersonic flows, hypersonic flows, or even flows wherein volume fraction is changing, wherein mixing is taking place, wherein combustion is taking place. We need particular. There are particular regions of interest wherein flow characteristic is very highly resolvable in that area, like shocks, like combustion, like droplet dynamics, etc. So in that region, we would prefer having a very fine, very fine resolution to account for every physics involved in that area. So that's why we prefer adaptive mesh refinement, which is AMR. Once again, it all depends on the physics, gradients, etc. And coming last to the sliding mesh. Sliding mesh, as can be seen in the vector graphics, the mesh in fact slides. This is particularly involved useful in places where different regions of area is moving simultaneously. Well, we have seen a case yesterday of diesel bore engine. It can be useful there. It will be useful in our present case, though in this case we are restricting ourselves to Chimera overset mesh, but it is a point which can be noted. Sliding mesh is very useful in the turbo machinery area. Once again, to read further on mesh of quite basics, you can refer to the wiki links shared. Okay, moving to next. Uh, Now let's discuss on turbulence. I'll be coming to the hands-on session very soon. It is very important for me to uh, tell you about all this before we solve. Okay. So here we are in this turbulence model SSTLM. We are solving mainly six equations. D is of momentum, XYZ momentum, then one is pressure, which is also known as the Poisson equation. Turbulence equation of K omega, which is turbulent kinetic energy specific dissipation rate. And the last two, intermittency and the rate eta. In open form, we can call the RAS function in the turbulence property, and then we can use the keyword K omega SSTLF, uh, so that open form knows we are using this particular kind of model. Next. Uh, this is the particular equation wherein towards you can see in this it's a form of Navier-Stokes equation, which it looks like the Navier-Stokes. Okay, so here gamma, here re theta, it's all accounted for. Now this is something professionals very who are very eager to know more, they can deep dive into it using the links shared here. One is the very good documentation provided by NASA on how this Langry-Mentor model has been solved. And the other is how OpenFOAM is implementing it. Now, coming to the simulation part. Okay. So, in our simulation, we have different dictionaries. Since we are almost on the culmination of the OpenFOAM workshop, we are very well aware of all this. I'll just revise all this. It's primarily, our objective is to have a very high quality body fitted aerofoil, which is obviously NACA 0015 with a course background, because we are more interested in areas towards the aerofoil, towards the wind turbine, than in the background. Okay. So first, primarily block mesh. Block mesh is used for overall. It is a dictionary which creates structured blocks, and it will be used mainly for the background. Snappy hex will be used to create complex geometry based meshing. And extrude mesh, it will be extruding a cell in the Z direction. As we all know, OpenFOAM is FEM based, so to add volume in a 2D dimension, in two-dimensional case, we need to extrude it in the Z direction by a unit distance of single cell. create patch once all, since we will be creating mesh independently of each other, there will be no single step mesh creation. So what happens is when multiple times we'll be implementing mesh commands, we need to be very careful in what patches are we assigning, because this patches will be something which wherein we'll be defining the boundary conditions. So that's why the create patch tool, merge meshes and topo set. Once again, for we'll be seeing how four different meshes are being created and then merged together, and then topo dictionary is used to assign variable the values. And the set fields, there are basically two straightforward, there are two ways in wherein we describe the values given to the input file. It can be explicitly mentioned as in a patch, or we can mention the values in every cell using the set fields dictionary. So let's start with the case. This is for the people who will be going ahead sometime later in the day. They need to be aware ki in each of the case. In our case, I'll first show you my present in the case dictionary. I'll be opening my terminal. Okay. So I have already downloaded this case. Okay. And in this downloaded case, they you will be finding mainly two folders. One is case directory and second is the report. This all run and permission all run is something what I have created for you people to explore later. First primarily will be entering this case directory, and I'll show you what are the different things in here. Here there are three folders: aerofoil C, pimple, and simple. So aerofoil C is something we'll be working on now. Pimple uses over pimple form, over pimple dy form, and simple uses over simple form. This over before the command is just to show that we are using a mesh of category overset, so that proper interpolation by the solver can be done when different meshes are stacked over each other, and proper calculations needs to be accounted. That's why a specific set of solver has been used. Let's enter the case directory aerofoil. I went using cd. I presume the audience is well aware of basic Linux commands cd, ls, because since it's towards the last stages of the workshop, it's the penultimate session, in fact. Uh, I'm skipping on that thing. So, to list more on the file contents in this, we have aerofoil overset, snappy hex mesh, we have the background snappy hex mesh, and the background overset. I'll be, and So once again, let me show you all the different dictionaries in the visual format, in the graphical format, in the icon format, whatever you would prefer to know. Uh, Aerofoil overset, snappy hex mesh, background overset, and snappy hex mesh. Uh, the intern has set a certain guidelines to follow, and that is mesh needs to be created in a step-by-step manner, which is first we would need to have a background mesh use it for the airfoil, and then we can use the overset. Then once again we'll have to create the background mesh using snappy, and then we have to combine the background overset mesh. Okay, I'll be showing you each step by step. Uh, so for the people who are very new, I suggest you please follow step by step, and do not refer to all run.pre, etc. Just manually enter the commands in the terminal when you will be doing it. Um, and I'll show what is the difference between each of the steps, why the four steps are needed. Uh, mo- Moving on. Okay. So, okay. Please make it a habit when you download the case. Please go through the README files. Yesterday also it was said the FOSSEE team has some guidelines while uploading the cases, and that's why one among them is having a very clear, crisp README. So please go through it. If you get stuck, revert to us. We'll be definitely helping you. Okay. So first step here, the user is suggesting, or the thing is, let's generate the snappy X mesh. Okay, and then uh, okay, terminal. So we'll be going to the readme.txt once again, nano, and then we'll be implementing the allrun.pre, opening the allrun.pre. The allrun.pre has all the commands which you need to put step by step for the successful generation. Okay, the first step, we have to enter the snappy hex mesh and run the all pre commands, or else we also have I also have something. mm, I can okay, interactive based. Uh, so once so there is this all run which I highlighted in the starting part. So this all run what is does is it creates something interaction based workflow. Uh, Highlighting time, I'll be referring to the switching to this as and when needed. So we have three cases which you saw. State. Please ignore this. This is a typing mistake which came in. It was inadvertent error. So we'll be running the case error file, and then this all is created using a bash script and the all run script using bash. So every step, everything is highlighted in what are we going to do after every command, what is the expected result, why is it necessary, or how you can implement yourself in your terminal. So this is it. I'll press enter. The first thing is all clean. Do you want to clean? I'll just skip. I skipped it. So that all run was basically to show you how you can be mimicking the exact thing without getting any assistance from us. Okay, and it has been taken care. Okay, every step is modeled perfectly. There might be bugs, there might be some issues, but it's mainly the case will be resolved. I hope I conveyed what I wanted to. Moving, let's switch back to the original version. Uh, and the manual CD careful. Now I'll be copying pasting the commands all each step by step. First, it's before pasting the commands, it is important I show you what is present in each of that. Okay, so in the aerofoil snappy hex, okay, first block mesh is getting created, and then we have once the background is getting created, we are fine tuning it and fine refining it. That's why the snappy hex and dash override represents whatever created previously should be neglected and rewritten. Okay. So I'll just copy this to commands instead of run. See, airfoil snappy. Okay. First command was block mesh. Done. And second was snappy. I need to show you how it is. So I'll be opening it using Parafoam. Please have a look at this, people. Normal two-dimensional with a unit dimension in the Z is been created. So this was the first step. Now the snappy hex. So this is how snappy hex iteration looks like. The way different parameters and different variables come into picture. We have to be very specific in defining all this. It is something. It is an advanced meshing utility of OpenFOAM provided, and it takes some certain, not certain, but really more than the word certain amount of practice to get familiarity with this kind of tool. So this mesh generation will take around 90 seconds on my system and will vary from system to system. Once it is created, we'll wait for some time and I'll show you. Once it is completed, I'll show you how the mesh looks like. Uh, Also, unlike commercial softwares, here there is no direct visual representation unless the mesh is properly made. So let's see how the mesh was generated. So previously it was just all rectangular square blocks. Now we can see specific regions of interest has been created. Okay, there is no, and this darker regions are is the area, is the specific area where we will be placing our aerofoils ahead. I'll just see. It is very important to note how fine the area is compared to the overall mesh. Okay. Now you might be perceiving it as a as a solid object, but later ahead we will be able to see how that portion is getting eliminated. So now moving on to the next thing. Once done with Snappy, we'll have to use the aerofoil overset uh, folder to generate further. For the aerofoil overset folder, once again, this here exists extrude mesh and create patch. I'll be quitting this, moving to the terminal. Until this was the first step of mesh generation. I'll be switching back to the previous directory and moving to aerofoil overset. First, I need to use the extrude mesh command. This implementation is very quick since we are only extruding by 1 unit in the Z direction. Particularly this, now you might be able to see how the solid region which was seen previously is eliminated and perfect aerofoils is coming into picture. You might see it is see through. Yeah. One thing to note is in the dictionary of extrude mesh, we are sourcing it. Everything has been sourced in order. So right now the source case it is referring ki please refer to this mesh already created in this directory and apply the necessary changes mentioned ahead. Okay. And similarly for create patch, now comes create patch. Here we are going to define the patches, inlet, outlet, and the walls. Create patch, override. Override is a function utility which offsets all the previous data and creates a new one in place of it. So to read out all this, we can see a new face of wall was added. Uh, Empty face was added, which is the front and back patch, and the overset patch is added. Now, since the airfoil generation is done, we'll be moving on to the background mesh generation. CD background. So the next command, next sequence in the background generation is block mesh and snappy hex mesh. Similarly to it, I'll show what the difference is in this time. Yeah, we are into this directory background snappy hex mesh. So first block mesh, mesh was created successfully. Once again, very simple. And now snappy override. Created. So particular small area was finely refined. Uh, So this was the change which took place in almost 1 second or 0.62 seconds. So the four steps of meshing are done. I hope everyone has followed the difference. We'll be seeing how the next process of combination takes place. So for this, we'll be shifting, we'll be entering the this directory. So we'll have to switch back. Right now, we are in the main directory of aerofoil. We'll have to enter background overset dictionary. So this okay. And here there are two things: all run and all pre. So first, all run pre needs to be all run pre needs to be run inside. Now four steps of mesh generation is done. Now we'll be combining it and running the solver. I hope the steps have been cleared until now. So once again, we'll be following this set of commands. This all things, it cannot be something which can be mugged up or by heart or by something. This is something you'll have to follow rigorously. You'll have to follow the readme files. You'll have to have the intuition on what command comes first, what command comes next, on what is that command creating basically. So this all can be only understood once you're doing it hands on. As of now, I'm just following the set of commands, copying, pasting it. It might seem like that, but it all comes with the experience of the user. And when you delve into it, you'll be realizing on switching and coming back and forth all every time. So this to overcome this, I also have the all run in the main directory, which will be bypassing it everything. And you just have to give in the terminal the input of yes, no, skip, integer numerical value, and all things will be done accordingly. So that was slight off topic deviation. So let's create all this. Okay, one thing you will be noting here is run application. What happens is run application is just a keyword here. If you follow this, there will be no terminal based output. Okay, it is something commonly used in the all-run scripts. But run application, what happens? See, extrude. I write extrude mesh. This number of finite steps have been generated. But when I just use a run application and combined with extrude mesh or any other function, I'll just get command run successfully and the last line. Okay, so that was the point of something I wanted to highlight. Extrude mesh is done. Next comes create patch, overwriting the existing patch. So this is something we'll have to merge. Let's see. I'll show you the mesh generation until now. This is not the complete mesh generation. Okay. I with this Input, I just want to highlight where at what point we have reached in the merging of the meshes. I'll show it again. The resolution wasn't clear then. So please note this is not the correct thing. Since it is incomplete, it is just showing some heterogeneous values in heterogeneous representation. We'll be hopefully seeing it perfectly later ahead. Okay, coming to the last set of commands, topo set. Topo set is can be found in the topo set dictionary. Here we are assigning certain values based or we are assigning field values in a particular region of interest based on the coordinates of that area. Um, yeah, that's it. Topo set. The cell set keyword here is something you should note. It is a particular commonality number of cells or a certain number of cells which have common feature can be assigned using cell sets. And then comes solvent pre. That was the final step. And now we'll be using restore zero dictionary. That is optional. Uh, if you already have a zero file, it's okay. Or else you can just copy paste it and rename it to zero. So zero.org means zero.original. Zero. So all the contents can be saved and preserved in zero.org, and you can constantly tweak in this. So let me go through all the subfiles, the files which we all as a beginner might be finding interesting. So the P file, which is of pressure. Here we are calling the value of pressure from a certain dictionary, from a certain input file. The boundary conditions are all you might be familiar with, the zero gradients and all. That is not something we'll be discussing right now. Uh, Eri theta values. So the user has decided to give an input value of 160.99 for initialization purposes. It needs to be initialized, right? Every CFD solving needs to be initialized with some certain values. So based on the discussion, based on the calculation, or based on the interest, this value might have been derived. Please note that. And something epsilon gamma is again initially gamma value is 1. That is in fully turbulence region. Data will be constantly changing based on solver. I'll be showing you the field values ahead. uh, and yeah, in the include is a folder which contains few information like flow velocity. Flow velocity is in normal to x direction with the value of 10 meter per second. Turbulent kinetic energy, turbulent omega, and turbulent epsilon value is also given. So that's why we are not explicitly mentioning it over here. Or else, if we would have mentioned it, we would just need to eliminate this keyword. I hope that was understood. And now I will be running the solver. So, uh, since this is very complex case, running this would take more than few days. I would like to tell you, I solved this case starting from zero with a delta t of 10 raised to minus 6. That is almost, there was interval of 1 microsecond after every solving. And with that very small time set, our objective is to contain the CFL values or the Cohen-Friedrich number to 1. Since this is a transient simulation, we need to have a CFL value less than 1 for the solver to progress capture correctly the flows. I'll show you how it is wrapped. The solver in our context can be found in this is the solver. Over pimple dy my phone. DYMF phone. Uh, over refers to the overset part. And everything related to the solver can be found on the documentation page for further study. So I'll be running it on a single code just to show how the simulation progresses. I have run the case until 0.0009 seconds, which took almost more than 48 hours. Please note that in a very good system. So I'll just enter this. So at every time step, at every right now the delta t is 3 raised to 3 into 10 raised to minus 5. It will keep fluctuating. Please note that because our time step is not fixed, though we are explicitly mentioning to keep a time step of 0.001, we are bypassing it with this keywords adjust time step and max score. Had it been 10, it would have a significantly larger time step. Had it been zero point 0.1, you could expect a reduction in order by 2. A reduction in that is right now 10 raised to minus 5. You could see 10 raised to minus 7 also to account for this CFL, or max score stands for max current number. So yeah, the solver will just now keep on iterating until very large time, until the end time is this is usually how this terminal looks like when the case has been resolved. So since we cannot wait for 48 hours to see the contours, we can see some using the already one, or using the already. I'll bring a stop to it. I'll show you the contours I have. Okay. Okay. So okay. So this case is resolved up to 0.00975 seconds. I'll show you how the contours look like at different time. Yeah. So first we'll be applying it. And yeah. So one among the things which as an observer or an audience should have clicked, there is something which is sliding out here, which is a pointed thing which comes out of the domain and enters it. This can appear like a sliding mesh, or it can be right to call it as a sliding mesh for some. But please note, there is just a rotation induced in the areas of interest. That is the area wherein the wind turbine or the aerofoil is getting rotated. No, the entire domain is not getting rotated. Just the specific region of interest is where you will see the rotation. Had we trim it further, we would have not seen this thing elongating out, emerging out of the domain. And please note, there will be no calculation error out here because the user has accordingly set the values. That's why it is something which can be noted as an observation. Nothing serious, nothing much on that aspect. So yeah, this is something the pressure contours. If I permit, okay, I'll be changing the U part. we are also able to see the vertices created. Okay, and if I set it to, and then gamma into values, not now. Yeah, so this is the turbulence number also, the transition turbulence number. Basically, all the fields which have been solved or which can be resolved by changing this is what I wanted to imply correctly. And now moving towards, it's almost done. So as an user, if you want to follow every step, you can just copy paste these commands step by step, and you will be able to replicate the exact same thing which is on my system. The user has also validated the performance with a benchmark NACA 00 airfoil also, a single airfoil. So validated the solver he used. Uh, Please note this is a single airfoil simulation which he demonstrated and not multiple. Yeah, this is the contour or velocity. Uh, yes, there will be a difference. You might be seeing the contours here and the contours shown in my system, primarily because the solving has been done for a very long time and then the contours are obtained. And however, that is not possible unless I have a very good workstation wherein I can keep it off for a very large number of days and forget on and keep doing my normal work. I hope that would be something appreciated. And last, the velocity contours was done. Now the pressure contours. So here you might be seeing the stagnation point is getting well resolved. The point zero, wherein the velocity is getting zero. And yeah, so towards I'll be concluding my case now. So if you want to explore more on the cases available on wind turbine, we can refer to case number 32, wherein once again VWT is modeled. 133, which is the present case, and 176. This case was done under Dr. Day's guidance. This is a very good case, and it will be very interesting. And this case is something which is done very recently. Um, it combines both the biological aspect that is inspired from the nature and the conventional aspects. So we all particularly insist on explore those cases. It will not take much of your time. We do not expect we would be very obliged and very happy if you could in, delve into it more. That will be the flotation of the workshop. But what happens is all you can do is download the case, just execute the all-run files, and see the results. You'll see is you will appreciate the things which OpenFOAM and is being able to do and handle. So yes, uh, now that was my last slide. I'll be sharing this automated files. I'll show you how the automation looks like in one single step, and then once I share it, you can download and just execute all the permissions. So here, primarily, there are two scripts. One is the all run, and one is the permission all run. What happens is once I transfer these files to you, all the executive permissions given to the all run, that is chmod plus x, wherein the system will be able to execute those bash scripts, will go away if those permissions are not given. So that's why to execute to give it the right and execute permissions, we this permission all run is there. So to execute the script dot slash permission all run, this will pop up. Once you write yes, you will be seeing wherein the all runs are present and the permissions have been granted successfully. So almost 23 files have been granted this permissions recursively. The script recursively searches for all the files starting with A or LLRUN or all clean, and then you have to run the all run script all run. Select the case. It starts with H-Darrieus vertical simulation. It starts with arrow. You can select any of this. Once again, please ignore the description in the first two. So I'll be selecting the first case. Uh, a general overview has been given, and then the workflow steps. We, as you might remember, we followed first entering the snappy hex folder containing aerofoil, the first step, then the overset, then once again background snappy, then the overset. The sequence I remembered was SO So that is what is happening here. S once again aerofoil O, background S, setting up O. Okay, that is just a layman trick. You can have yours as well. So do I want to run the all clean? All clean will eliminate or delete all the files which have been there. So I'll be moving next. So first step, generate aerofoil mesh using why? Because we are creating NACA 0015 plate with approximately 45,000 cells in the boundary layer. Accounting, we are also taking care of the Y plus values. That's why this much number of cells. So it will also be shown run block mesh plus snappy hex. So just write yes. It will keep working for the next 90 seconds or unless or until the amount of time you see. I'll let this run, then I'll show. I've also added this feature wherein after every step is getting executed, you will be able to visualize it in the script itself. Or otherwise, you would have to go to the different directory, navigate and open it, then enter parafo to visualize it. But the script would bypass that. This is for people who this is for people who like to skip the hard work and get things automated. This days I'm just bypassing everything. Okay, until this case is running, I'll share you the download link. So this drive modified case with automation. Uh, so I've shared the drive link in the chat box, and I'll also be sharing the original case. Please note I haven't changed any of the physics involved. It's just the execution steps. It was generated once again in 80.83 seconds. If you want to see the generated mesh, just type yes. Also, this command, you might be, it will vary from user to user. Right now, I'm in this directory. You might be in some other directory, and this should change. Okay, so this is until this region, this is the directory, and this is the command paraform built in. Simple paraform also works. Yes, paraform will pop up. If you guys might have remembered, this was the very first mesh which we saw. Okay, then press enter to move to next. It says, do you want to go to the next step? I would say yes, I very much want to go to the next step. It is something very quick. Once again, this will be, so what I showed you in the last 15, 20, almost half an hour. I could have used the shortcut and wrapped up in 5, 10 minutes. So that is the beauty of the script. Yeah. So I'll not run further because you know what happens ahead. All there are two more steps, and then running the solver either on single core or on parallel. Okay, I'll just press Control C, and with this, I'll I'll rest my case. It was nice presenting to you. Thank you. Over to you, Paris.
Yes, yes. So any more questions for Pranay?
And there is a question in the chat box
Yeah.
regarding how to change the rotation speed. So if you have any idea about it, you can.
Yeah. Okay. I'll just highlight the dictionary if it is there. Should be. Yeah. So if I'm not wrong, you will have to call the dynamic mesh dictionary in the constant folder. And omega. Omega is the rotation value which we will be given. So in the background overset folder, in the constant subfolder, we have a dynamic mesh dictionary. And into this, we are calling the dynamic mesh overset library, FV mesh library. And in this, we have the rotation speed axis. I am not very much sure on the units, but in general, the origin is defined, the axis X, Y, Z direction. And omega, it should be radian per second, or it could be, yeah, that is the speed part. I'm not very much sure, but yes, this is, you just have to change this value to get the desired rotational speed. I hope that would clear the doubt.
Okay, so with that, I think we can move on to the next part of the workshop.
Thank you.